Good people, I know that you're all looking forward to the point where you can start actually writing programs and making things work, but I'm afraid before we do that, we have to do some of the boring preparatory work first. You're going to need software in your PC to help you create the program. You're going to need more software to handle the transfer of your program from your PC to the chip. And if you're designing anything at all with a chip, you need to have some hardware around it. If you're going to flash an LED with it, then it needs to be connected to an LED, etc. Before you decide on a final design of your circuit, you're likely to go through several iterations and trials and reconnections and remaking the circuit. So the best way of doing that is with a breadboard. If you haven't got a breadboard, or if you're not familiar with this, then get one. Breadboards come in various different sizes. I would recommend getting the larger one because it allows more scope for connecting bigger circuits. Very cheap as well. There's an advert that I found here on eBay for a breadboard, the big one, with a power supply and with all the cables. The cables are flexible, but they've got solid ends on them, so you can plug them into the breadboard. The whole thing for £5.65. Now, usually £1 translates pretty accurately into $1, so you can expect to spend $6 or a bit less. The way the breadboard is connected, it's got long rails down the side there, so you can connect power into those, and then from there you can connect power onto these holes in the middle. The holes in the middle have connectors that run up and down like this, and there's another rail along the bottom for power. You can probably see these little pegs. They fit into little holes on the other side, like little dovetail holes, and you can put breadboards together like that, so you can build bigger circuits on them if you need to. Also, the power rails detach. They're also on dovetail joints, so you can take those off. So you could, for example, take these two center ones off and have this section right next to this section if you wanted to. There's a dedicated type of power supply for the breadboard. Now, this connects into USB, but the USB doesn't carry any data. It only carries power, but it will supply a surprising amount of power, actually. Enough, in fact, to make an ATtiny chip smoke and melt the breadboard if you plug the chip in backwards. It has a couple of jumpers on it there and there, where you can jumper 5 volts or 3.3 volts to feed your chip. It also has a power input here. It just says DC in. It doesn't say how much, so you would need to look at the specification for that. I haven't actually used it. I just used the USB. And it's got a switch on it where you can switch it on and off, so you don't have to keep plugging and unplugging the USB. Now, as I said, you're going to need some hardware and some software in order to program the chip and get the program to the chip. And I'm not going to cover that. I'm going to direct you with a link in the description down there to a video by a young guy who calls himself TannerTech, and he describes how to load the Arduino IDE. IDE means Integrated Development Environment, and it's got an editor which allows you to write programs and a compiler which allows you to make them into something the chip can understand. And he describes how to program an Arduino Nano like that. There's the Nano, and he programs it to become an interface between the computer's USB and the TWI on the chip. All of the Atmel AVR chips have 2 pins that are dedicated to a TWI or 2-wire interface, and it conforms with the I2C communications protocol. It's an ANSI protocol. It's interesting where that comes from. I2C was before that I2C, but a square is a superscript 2 and it's more difficult to write on a keyboard, so it became I2C. But I2C came from IIC, which means Inter-Integrated Circuit Communication. So TannerTech describes how to use the Arduino IDE in order to make a converter using the Nano to send data to the chip. The software inside the PC that actually handles that serial transfer is called AVRDude, and that will come as part of the installation of the Arduino IDE. TannerTech builds his programmer on breadboard, but I do recommend that you make a dedicated one because you're going to be using it a lot, and there is mine. So there you see the Arduino Nano on the top. I'll just take that off, and it's on a couple of sockets which are commercially available. You'll have to get those, look them up on eBay or your favorite source of gadgetry. And underneath the chip you can see that there's wires running in there that connect the chip socket to the socket for the chip you're going to program. There's also a capacitor there, a 10 microfarad capacitor that has to be connected on the reset line of the Arduino Nano. The other big piece of software that we're going to need is Atmel Studio-7. Studio-7 is also an IDE, an integrated development environment. It gives you the editor and the compiler, but much more than that, it gives a simulator. So you can simulate the chip in software, and in fact before you ever get your chip you could use Studio-7 to start programming. The link again is down there in the description, so go and get that now, and when you come back we'll have a look at it. This is the initial screen of Atmel Studio. I'm just going to load something that I wrote before for the sake of showing you around. So this screen shows you what they call the start screen, and you can see it at any time by pressing View and Start Page, and it shows this page. You can open a new project, or you can open a project that is already recorded, stored. So I'm going to open dec to bin, which is a decimal to binary routine that I wrote as part of my timer routine. There it is. So here we have the program. You can see there's not very much of it. It's just a short little routine. It's part of a much bigger thing. To compile it, if I simply press the single step key, which is F11, then it will compile and perform the first single step. There we are. So it is showing this location here. It hasn't actually executed the first instruction yet. But what is it showing? It's showing the program down here. You can move this up and down with a cursor. It's showing here the memory. Now at the moment it's showing data IRAM. There are three kinds of memory on the chip. There's the flash memory, which contains the program and which is non-volatile, which means that it doesn't lose this memory when you power the switch off happily. Be a shame if it lost the program. These instructions written down in the program are each 2 bytes in memory. So each one of those instructions is 2 bytes. That's the first one, that's the second one, the third one, etc. So the entire program that you see there fits in there, a few addresses. The registers are kept in RAM. It's static RAM, and the first 32 bytes of it are used for the 32 registers, R0 up to R31. We can demonstrate that the registers are in here because the registers are also displayed down in this section. Now if I take R0 and I give it a value of let's say easy. Okay, the easy has now come up in the memory up there, and the AA that I put into memory is now displayed in register 10, and if we count that, that's register 0, register 7, register 8, 9, 10 has taken on a value of able able. The next 64 registers are these down to address 60. These are the I/O registers which control the functions of the chip, the various internal peripherals, what your setup is, what your profile is for the chip. From address 60 downwards is available memory. You can use that at your discretion. And if we look at the data sheet, there we see the features of the chip. Pin configurations, that's what the chip looks like and what you can connect to it. And down here we see the AVR memories, and it says something about them. You can read that. And as we see the program memory, there are 3 sizes given here. This is for the AT25, the AT45 and the AT85. So in our case it goes up to address Fox Fox Fox, and it is a 4K memory. The data memory, static RAM, as it shows, it has 32 registers from address 0 to 1 Fox. It has 64 I/O registers from address 20 down to 5 Fox, and from address 60 is available memory, and that goes down in the case of the AT85 to 25 Fox. The stack pointer points to the end of memory, and the stack grows towards address 0. Every time you call a subroutine, it puts the address that it is leaving onto the stack so that it can find it to go back there when you return from the subroutine. So really and truly, if you go 10 subroutines deep, that's a lot, and that would 20 bytes into memory. So that's memory. The other kind of memory that we have on the chip is EEPROM, and until now I have never used the EEPROM, but I believe that writing to it is very similar to writing to the program memory, and I did use that on my timer because when I've programmed a time in, I want to put it in the program memory so that it doesn't get lost when the chip powers down. We will be covering that during the course, how to write into program memory, and I believe that writing to EEPROM is very similar. In this frame here we also have the possibility of I/O. So these are the various I/O devices. Here we have the I/O ports are very important. When you switch I/O ports on, you'll see they go red here initially. When they first get switched on, they go red, and then they just get a red ring around them to show that they are on, but they haven't just been switched on. They only go red after the instruction that switches them on. And we can also operate these ports, so we can actually set them like that to do things with them, to force your pseudo chip to do things. In other words, if your real chip would have raised a signal on this, you can simulate that by clicking the port. The timer counters, we'll be using this one, and there's the output compare, which we will see operating, and the value of the timer, and you can see all of its internals down at the bottom of the screen here. There are lots of registers used in the timer, and you get a full breakout of them. As the program is proceeding, over here we see that the program counter is all zeros. That's because we're pointing to the very first instruction. If I single step that a couple of times, there you see I've executed 2 instructions, and now the program counter is pointing to address 2. That is address 2 in the program memory. So there's address 0, address 1, address 2. So this is the instruction that it's about to execute. The stack pointer is at address 25 Fox. The X, Y and Z register, or Z register if you're American. These are special purpose registers, and they are each composed of two registers. So there's the X register, is registers 26 and 27. The Y register is 28 and 29, and the Z or Z register is R30 and R31, and they are registers that can directly address memory. So when you're writing into memory or reading from memory, you use these registers to do so, and there are some special instructions for them. So you can write from X plus, for example, and it will write the contents of some register up here to the address pointed to by X, and then X will automatically increment. You can also do a pre-decrement, so you can write to minus X, and it will first decrement the X register and then write to the byte that it finds there. These are used for implementing your own stacks. So if you want a data stack for passing data to subroutines, for example, you can do it with these registers. The output files show the dependencies here. At the moment, we're showing main. That's this main here. You see the output file is main, and it says up here main. Sorry, that's my start bar. That's main. We can also show this dependency here, TN85def. These are the definitions for the AT85 chip. I really want that in there. So there we've got main, and there we have the definitions. And you can use these definitions, for example, there, port B0 is pin 0 on port B. This chip only has port B because it's only got a few legs, and port B is the one that they have chosen. Some of the bigger chips have port A, port B, port C, and each one has 8 bits. And you can set the direction for each bit, whether it's in or out. You can set whether it's got a pull-up resistor on it, all sorts of things you can do on the ports, and you can address them by these definitions in this file, and you can see there are lots of them. We'll be coming to some of those. Up here is the status register with the various bits in here. Now when you hover the mouse on these, it shows you in a tooltip what that bit is for. So for this one, for example, it says half carry flag, but unfortunately that doesn't copy onto the video, so you won't be seeing that. This one says sign bit, V is the 2 complements overflow flag, N is the negative flag, so if the result of the operation was negative, this one will be red. Z is the 0 flag, and C is the carry flag. I is the global interrupt enable, so if you switch this on, it switches interrupts on, and if you switch this bit off, it switches interrupts off. So and there are 2 instructions for doing that, so it makes it very convenient if you're going to do something that mustn't be interrupted. It's got to be a fairly short routine, but if you're doing something that mustn't be interrupted, then you can switch the interrupts off, you can do your thing, and then switch them on again. The T is the transfer flag, and there are various instructions that benefit from this, because you can transfer a bit to that and then transfer the bit to another register. We'll see that later on. The cycle counter says 1 because we have executed 1 instruction. The frequency is set to 1 meg. You can set that to anything you like. It doesn't actually know, but you set this to whatever speed you're going to run your chip at, and it uses that value to calculate how much time has been spent in the execution of your program up to this point. So if I execute another few instructions, you can see the count here has gone up. Some instructions take more than 1 clock cycle. For example, a jump takes 2 clock cycles, but it will keep track of how much time has been used so far. If we execute down to There, clear R0. Now if I execute, this says 19 microseconds. If I clear R0, that goes to 20 microseconds because the clear takes 1 clock cycle, and the clock cycle is set to 1 microsecond because we're running at 1 megahertz. If I execute the jump, RJump, you will see that this goes from 20 to 22 because the jump takes 2 clock cycles. On the larger chips, we have a much bigger memory. So they have a jump instruction, JMP, which will jump to anywhere in memory. On this little chip, we have an RJump, which means a relative jump. So we jump relative to this one, plus the contents in a 1 byte variable. So the jump instruction, if you try to execute it on the AT85, doesn't work. It's an invalid instruction. Similarly, a call to subroutine has to be an R call, a relative call. On the bigger chips, they have a call instruction, which will call an instruction far away in memory. But in this one, you can't get very far away in memory, and they only use the R call. Right, I think that about covers a walkthrough of what this program will do. There's a little bit of setup that you must do. If you go to Tools, External Tools, it brings up a frame. Now in here you need to put Arduino Nano COM6 in the title. That is just the title. It's useful perhaps to have the right COM port. You find out your COM port by going to Control Panel, Device Manager, and if you look for ports down here, it would be in between network adapters and processors because it's alphabetical, and there are no ports shown. However, if I plug my programmer into a USB, it now shows ports, and if I open that up, it says USB serial. CH340 is the serial chip on this on the Arduino Nano, and it's on port 6. That's quite interesting because if I plug it into a different USB port, it now comes up on COM5. So it's a good idea to get used to always plugging it into the same USB port so as it comes up on the same COM port. COM6. And that's this COM6 here. Command must be the full address of AVRDude.conf. Now AVRDude you got with the installation of the Arduino IDE. If you press this button here, you'll be able to search for AVRDude, and it is in your C drive. Program files 86. This is where mine is. I can't guarantee that it's the same on yours, but perhaps this will help you in any case. Arduino, hardware, tools, AVR, bin, and there it is there. So I'm just going to press cancel, you would press open, and it'll fill that in for you. Mine's already filled in. Then AVRDude is driven from the command line, and you put a whole pile of parameters on the command line. So if you were just going to run it from the command line, these are the parameters that you would put you would put AVRDude and then all of this lot as flags. Now, I have copied these in the links below. So there again, load that and paste it in here. You can go on Google and just search for AVRDude parameters and it'll find them for you. It's worth making a copy of that web page and just store it locally so that you can understand what these are all for. When I first installed this, I didn't realize that these were parameters going to AVRDude. I thought that these were parameters for Atmel Studio-7 and it confused me for quite a long time. Right, so take this line and paste it in, and that should get you programmed to use AVRDude and to use Atmel Studio-7. Okay folks, as you can see, it's got dark now. You can barely see me, which has certain benefits. I think that about does it for today. So in the next lesson, we'll start and write some programs and single step them, see how it all works, and I'll show you how I get the program from Studio to my chip.